Good afternoon, everybody. This is Stephen Buttars again at VisualSonics headquarters here in Toronto. Welcome. We're just ready to start our webinar today. So today, myself and Drew Heinmiller, who's another product manager here, will be going over some product updates focused on our version 3.2 release of software for the Vevo 3100 and LAZR-X system, and also for Vevo LAB. We've got some great new additions and changes and improvements, developments, and tools to talk about in this webinar. So just some notes about the webinar as we get going. A recording of the webinar is being made right now live and will be made available shortly after the webinar wraps up. All of the phone lines and computer audio lines are muted. If you do have questions, please go ahead and use the Q&A button on the Zoom meeting interface to submit those questions. We will have some time at the end of the session to try to get to those questions. So we're expecting maybe about 45 minutes, maybe a bit less for a presentation, and then we've got lots of time available at the end for questions. Your hosts today, myself, Stephen, and Drew. Again, we're both product managers here at VisualSonics. Myself, I'm focused on the ultrasound component of our system, and Drew is focused on the photoacoustic component of the system. So just a really quick overview. We'll just give an overview of the VisualSonics product family, excuse me, and then we'll start into some of the highlights of our latest software release, again on Vevo 3100 and LAZR-X imaging system, and then also on the Vevo LAB Workstation software. Because a lot of the, some of the really neat new features are available on the Vevo LAB Workstation, we'll actually flip back and forth a little bit between the presentation and Vevo LAB itself to do a live demonstration of some of these tools. And then, of course, as I mentioned, we'll have a Q&A session at the end. So this is the currently offered Vevo imaging system family, the Vevo 3100 and 3100 LT imaging system, with the then the LAZR-X photoacoustic extension to that system. And then, of course, we have the Vevo Mmode clinical imaging system, which has regulatory approval in quite a wide number of jurisdictions now for use in the clinic. The preclinical products, of course, I've mentioned Vevo LAB a couple of times. The data from them can be fed into the Vevo LAB Workstation for post-acquisition analysis. So just to remind everybody, what makes VisualSonics systems so different from clinical ultrasound systems is really the frequency. Ultra-high frequency ultrasound, which gives you very high resolution. So we're able to look at these structures in small animal models, and then, of course, in humans with the Vevo MD system at a very, very high resolution, millimeters versus centimeters. So going to high resolution gives you this order of magnitude increase in resolution that you're able to achieve in your images. And then from then, of course, everything sort of falls out from that basis with Doppler and nonlinear contrast and photoacoustics. So all of the other modes and capabilities that we have on the system. You may have noticed, sort of longtime users and customers, that I mentioned the currently supported or currently available system family starts with the Vevo 3100. Our older systems, the Vevo 1100 and 2100, we have ceased selling those systems. They are still supported. So for those of you, quite a number of you out there who do own 2100 systems, there is support still available for the 2100 systems going through until the end of 2023. So we've got a fairly long support period available to you. Quite a number of differences on the 3100 versus the 2100. Certain things like 4D mode, which is not something that was not possible on the 2100 platform. Image processing, where we're reducing some of the speckle and the noise that happens sometimes in these high frequency images to really try to bring more clarity to the tissue, the anatomy that you're seeing. The transducers are different as well between the two systems, much lighter, more ergonomic. and with some increased sensitivity and flexibility. And then a huge difference on the system is the touch screen control system, which gets away from the big old keyboard that the 2100 had. This is the touch screen adds quite an impressive boost to the flexibility and the throughput of speed on the system as users adapt to it. Now, along with the 3100 and 2100 change is a change between LAZR and LAZR-X. And I'll ask Drew to step in and comment on some of the differences here.
Sure, thanks, Stephen. So probably many of you are currently using the LAZR or possibly the 2100. There's significant improvements between the Vevo LAZR and the Vevo LAZR-X system. And what we're kind of showing here are the two lasers, actually. So the laser technology, which is the core of the photoacoustic imaging technology, is really about the laser. And the new laser, we have new laser technology. It's much faster imaging. Much more sensitive as well. There's higher energy that gives us much better sensitivity. As you can see here, it's also a lot more compact, so a lot more sort of maneuverable. We've also changed a lot about how we deliver light. So on the Vevo LAZR, we had the fiber optics, which deliver light into the tissue. They were integrated right into the transducer itself. What we've done for the Vevo LAZR-X is separate the transducer itself, the MX series transducers, from the light delivery. So we now have jackets which we clip over top of the existing transducers and deliver the light. That allows a lot more flexible light delivery. So we can use different widths of fibers essentially, and really match the application to the light delivery itself to get, again, much better depth and sensitivity in certain cases. And then we've also integrated a lot of hardware and software tools for doing different kinds of applications. I'll talk about the applications in the next slide, but really integrating things like the UI for our injector pump, so you can do remote injections, and integrating tools for doing phantom imaging, so you can characterize photoacoustic contrast agents. These are all part of the Vevo LAZR-X system, which do not exist on the 2100 system or the Vevo LAZR.
Great, thanks, Drew.
I just kind of want to go over, again, just to remind people, in case you're only working on one application area, I just want to remind people of the different application areas we have. There's obviously the cardiovascular part, and Stephen mentioned 4D imaging, for example. There's also strain imaging, being able to measure strain in the myocardium, as well as strain in the vasculature. So that's our vascular strain Vevo Vasc package. Being able to do things like, of course, the usual velocity measurements as well. In the cancer space, it's everything from using image-guided injection to induce tumor models, right down through screening, sizing of tumors, volumetrics, down into hemodynamics, looking at perfusion with microbubbles, blood flow, again, and oxygenation with photoacoustics, and then getting right down to doing some molecular imaging applications with the photoacoustic imaging system. There's also some neuro applications which we've developed, especially with the Vevo LAZR-X system. Having that extra depth and sensitivity allows us to do really nice sort of neuro imaging. And the example that I have today for the Vevo Lab demonstration of the new features of the software actually focuses around a case of neuro imaging. So you'll see a little bit of that later. There's also developmental biology applications looking at health of the developing fetus, from everything from actually imaging the fetal heart, blood flow, perfusion, doing image-guided injections for things like drug delivery and other things, and then looking at things like placental oxygenation with photoacoustic imaging. And then a huge range of other applications as well, doing things like lymphatics, looking at tissue constructs for tissue mimicking scaffolds and these kinds of things. And I put on the bottom there a couple of slides. One is a zebrafish image. So, this sort of speaks to the range of animal models, going everything from zebrafish, and the image on the left there, to the left of the zebrafish, that's actually a pig spinal cord. So this sort of speaks to the flexibility of the system for doing a very, very wide range of applications, but also a wide range of animal models.
Great. So I wanted to just highlight really quickly, I mentioned a couple of times the Vevo LAB Workstation. So just to talk about that, so Vevo LAB Workstation software is a separate piece of software that's available to work with the imaging data. So this is really kind of a centralized data management and analysis environment that is become kind of a product on its own that we've really sort of used as a platform to develop a lot of really interesting measurements, calculations, and tools to manipulate and analyze data. And just to highlight again the different systems that we've been talking about here, everything from the 3100 and LAZR-X, going back to the older systems, the 2100 and LAZR and the Vevo 1100, data from all of those systems is all supported by Vevo LAB. So going forward, we will continue to update Vevo LAB and it will continue to move forward, but we will do our utmost to maintain the compatibility to the formats of the data from those earlier systems. So if you're out there, working away on your 2100, even though, there's really not going to be new software or new tools added to the 2100 system per se, still do try to keep your Vevo LAB workstation install up to date, and you'll be able to access some of the great changes and developments and new tools that we are making available. So to switch over to the system side of things, I wanted to discuss something that's new in the non-photoacoustics area with the version 3.2 software. So again, this is specific to the 3100 and LAZR-X system platform. On the 4D and EKV acquisition, we've made some improvements to the respiration gating and R-wave detection algorithms. So this helps to improve the handling of some animal models have a particularly unusual respiration or ECG patterns. We've made quite a few changes to the way that the data are acquired and processed to try to deal with that. And another change that we were able to make was previously, sometimes on the system, once in a while, the physiological signal would drop or become unreadable in these situations with sort of unusual respiration or ECG. And if the acquisition stopped prematurely, the data that had been acquired up to that point would be lost. That doesn't happen now, where we actually were able to figure out how to retain those data from that partially completed acquisition. So this is kind of nice when you sort of get to the end and you're almost at the end and you've got like the last 10 seconds or 20 seconds or something, and then something happens and you've lost that data. So that's not happening now. Looking at the photoacoustic side of the equation, with some of the changes and tools that are here, I'll just Drew to comment.
Sure, yeah. So a few small things on the photoacoustics acquisition side of things on the system. There's a couple of measurements that we've integrated into the system. I'll talk about a little bit about those later and actually demonstrate them, at least in the lab setting, a little later. But this is a histogram of SO2 measurements, as well as being able to display a range of oxygen saturation measurements. And I'll demonstrate that a little later. As well as the unmixing curve import and export. So you've always been able to import and export, spectral unmixing curves into the system to do spectral unmixing for your photoacoustic data. We've just opened that up to allow for customized curves via CSV files. Finally, because the system can be used without the enclosure, so it can be essentially a handheld imaging system, we added one small UI feature, which is just a flashing or pulsing, I should say, laser symbol to indicate when the laser is actually firing. It can be sometimes sort of difficult to know when it's firing if you're wearing the goggles. You're not able to see the light. The goggles are blocking the light. So this is just a nice indicator so that you know for sure when the laser is actually firing and when it's not.
Great. So moving over to the Vevo LAB Workstation side of things, one of the big changes and additions that's there now for standard ultrasound data is AutoLV for short axis Mmode. Now we've had an AutoLV option for some time that worked on Bmode long axis images. That's now been extended to the Mmode short axis images. And this is an artificial intelligence based tool for measurements that I'll talk about in a little bit, and I'll also demonstrate on that when we switch over to Vevo LAB. There are multiple areas of 3D improvements. A lot of these tools are useful across 3D acquisitions in all different modes, but I think they have a lot of utility in photoacoustics.
Yeah, and I don't want to go into too much detail here because we'll actually be demonstrating them. But yeah, these are significant improvements in the ability to do 3D measurements, multiple 3D measurements, and copying and pasting those measurements.
And the same with the oxyhemo tools as well.
Yeah, I'll show that.
Okay, great. We mentioned the unmixing curve import and export. Within this release of Vevo LAB, this is the 3.2 release, there are updated versions of the Vevo Strain and Vevo VASC analysis tools. Not a huge set of changes there in terms of capabilities or user interface, but more sort of refinements to the user interface and the user experience, and some changes to improve the stability and the speed of the system of those pieces of software and the flexibility. So these are Vevo Strain and Vevo VASC. The tools are kind of held within Vevo LAB, and they run within Vevo LAB. So again, there's some changes in there to just improve the user experience. Another nice tool that's been added to Vevo LAB that I'll show as well when we get over to the Vevo LAB demonstration is an editor for the burst marker, and this is specific to nonlinear contrast images where you've done launched a burst pulse to do destruction reperfusion imaging. So I mentioned off the top of that slide there that the AutoLV tool had been extended to short axis, and that the AutoLV tool is an artificial intelligence-based tool. This is just a couple things that I wanted to mention about artificial intelligence. These terms, artificial intelligence, machine learning, and deep learning, are certainly terms that are in the forefront of technology and technology discussions these days. And these tools are being employed in many different areas. In medical imaging specifically, there seems to be a lot of significant amount of interest in artificial intelligence, machine learning, and deep learning tools. And some of the things that we're hearing and seeing is that the expectation is that some of the traditional methods of data management and specifically data analysis may be displaced by some of these tools. So our AutoLV, what we call our AutoLV measurement tool, or tools actually now, because it is two separate tools, uses neural networks and image processing algorithms to do measurements on images for you. And these algorithms have been trained with sets of data that we have collected up from ourselves, from various customers. And we've had our in-house experts our application scientists go through and make sure that all of the measurements that are placed on those images are correct before those measurements are then passed into these algorithms for training. So the Bmode long axis version of AutoLV has been out actually for 2 years now, and had a smaller training set. Again, for this version of 3.2 now, we've extended AutoLV to work on Mmode short axis with a very large set of training data to help to refine the algorithm. And this new functionality, this Mmode short axis functionality, is actually included with the existing AutoLV option. So if you already have AutoLV and you upgrade to your Vevo LAB to 3.2, this functionality will be there automatically added on. Or if you acquire the AutoLV functionality in the future, it'll include both the Bmode and the Mmode functions. And internally, research and development into artificial intelligence-based tools for data management, data analysis is ongoing. We have a number of different projects that we're working on that are in various states of development. And I would say that expect to see some further updates to either some of these tools or new tools coming with the next major release of Vevo LAB, which is planned for next calendar year, 2020. And I think at this point, with the power of these tools, we will continue to see going forward the functionality, the availability of them expanding and growing as we start to move out into that area. So we're going to switch over to Vevo Lab now. And we'll take a quick look at some of the AI-based tools that I was just talking about. So I'll show what the Bmode long axis tool looks like. So this tool, this existing AutoLV Bmode long axis tool, is designed to work only on long axis images, Bmode images of the parasternal long axis of the left ventricle. And it's also designed, the tool is expecting to see the apex on the left and the base of the heart on the right. This is just kind of a standard thing that it's expecting to see. So if you, don't be afraid though, if you have images that were acquired the other way around, they can actually be flipped by clicking this little invert image button right here. And so you can flip your images left and right. So to use the Bmode long axis tool, all we need to do is start on an R wave. So we've got an R wave down here at the right side of the physiological strip. That corresponds to what we're seeing here in the frame. And once we're there, we just click on the AutoLV button that's up there on the toolbar. The system, the algorithm will look at the image and it will compare it to that library of traces and some of the other tools that are there, and it'll report back what it sees as a tracing. So we've got the endpoint of the tracing here in diastole, and it's placed all of these contours for us all the way through to end systole. And you can see all of the functional parameters that have come out from that. So effectively a one-click solution. Once you found that R wave to start, you just click the AutoLV button and it goes ahead and does the tracing for you very, very rapidly. So what's new and exciting here in 3.2, in this version 3.2, is that now we have an AutoLV button available here when reviewing Mmode. So again, this is very specific to short axis Mmode. It's expecting to see short axis Mmode, expecting to see the endocardial and epicardial, anterior and posterior walls in this particular orientation. And to use the tool, all we do is click the AutoLV button here at the toolbar, click where we want to start the tracing and where we want to end the tracing here, right click, let the algorithm do its thing, and it very quickly will give us its proposed, what it sees as its proposed wall tracing here. And then again, it will report back all of the functional data, the LV mass, and some of the wall thickness data. And I should actually mention, you can configure, if you go click on, right click here on the measurement reporting block and go to properties, you can actually configure which items are reported here. So if you're not interested in the wall thickness, you can always hide that. It is shown by default though. So very rapid analysis and very consistent analysis. So I think there's kind of two areas which are very interesting for these artificial intelligence-based tools, and that's speed of analysis, and also to take some of that intra and inter both operator variability out of placing measurements that we see from time to time by sort of taking that human element out of it and just using those algorithms for analysis. So I will switch back from that to the photoacoustics section, and I'll hand it back over to Drew.
Great. Thanks, Stephen. We've sort of talked about these things already. So what I want to do is I want to describe the example that we're using in the live demo of the system. This is actually some work that was done with Alex Kwan at down at Emory University, and he had a model of stroke which involved it was a hypoxic ischemic model of stroke, where essentially you would ligate the common carotid artery, in this case the right common carotid artery, and then have the animal breathe a hypoxic gas, so 7.5% O2. The combination of these two things was able to induce a stroke via these sort of micro infarcts in the brain. So we did a whole bunch of imaging during this study. This was published in 2015 in the journal Stroke, by the way. Unfortunately, this video isn't playing, but this is a sort of how we did the ligation. And I put this here just to point out that this was actually a reversible ligation. So after hypoxia ischemia, you would alleviate the hypoxia by having the animal breathe medical air, and then you could just pull on these two sutures and release that ligation of the common carotid and have blood flow supplied back to the brain. So we were doing mostly coronal sections of mice in this case. And then I'll switch over to lab there, find the study. Okay. Bear with me here for a second. So here's the stroke study. So the one thing I want to just show you very quickly, there's a few features in here that, that are not necessarily totally new to this release, but I want to point out. So this is a coronal section. This is imaging of the mouse brain. And you'll see here, I'm just going to stop it for a second, but you'll see here there are these markers. Okay, there's one here toward the left and one here toward the right. So those are frame markers that indicate when the ischemia occurred and when the reperfusion occurred. So this is essentially showing when we pulled the two sutures to ligate the right common carotid, and then when we released it. So here's the ligation, and I'm just going to go back here for a second. I want to point out on this image, the blood flow here, which is sort of heading, this is around the circle of Willis, it sort of switches from going away from the transducers to toward the transducer. So the direction of flow changes, and then you have an impairment of flow on the right side with the right common carotid ligation. Now here it's coming up to the point where the ligation was alleviated, and you can then again see changes in flow that are happening in both of these areas in the color Doppler image. So this is just kind of neat that we could actually do this ligation. It's a fairly non-invasive or minimally invasive, I should say, ligation, and we could see that live. So that was kind of neat. We also did some imaging using the photoacoustic imaging. This is now looking at oxygen saturation. It's a parametric map of oxygen saturation in this case. And the red is basically indicating more highly oxygen saturated areas, with the blue indicating lower oxygen saturation areas. And similar to what was done in the previous thing, we were just imaging while we're doing this ligation and the reperfusion. So you can see here there's signal that drops off significantly on the right-hand side, especially in those cortical and subcortical areas. That then recovers. A little bit harder to see. The frame rate's a little lower in this one, but I drew two regions of interest here in the right and left hemisphere. If we right-click and go down to the region graph, you can see the difference in the right hemisphere drops off significantly. This is SO2 on the y-axis here. You can see it drops significantly and then comes back upon reperfusion. And actually, while I was putting this together, I learned of this this feature. One of our developers put this in. You can show these frame markers on the graph itself. So this is really nice to be able to show, okay, that's when the ischemia, that's when we induced ischemia. That's when we alleviated the ischemia. You can really see those changes there. Another nice thing here is this, the range. So this is a new tool. This is a 3.2 release, a new tool, this SO2 range. So we can actually choose to see what range of SO2 we actually want to visualize. So let's say here's 50% to 100%. Okay, so we can see as we go through that Cine, there's the ischemia. So we're looking at the higher oxygen saturation values to see how those are affected. And alternatively, we can go to the lower values too and say, okay, I want to see the lower values. What happens with those lower values when we do the ischemia and the reperfusion. You can see things here. This SO2 range display does not affect the measurements. Okay, so you're still going to have your measurements as if you're seeing the whole thing. It's just for visualization. Now this tool, this SO2 range tool, exists on the system itself. So if you want to just look at a range and how that range of SO2 is changing over time live, you can do that on the system. Okay, now I'll go over. So we did that. We just showed the ischemia reperfusion, and then we did this in 3D. So we induced the ischemia, and then we did 3D scans. So in this case, I'm going to bring up the 3D color Doppler scan. So I'll just play through this here, but this is a 3D color Doppler, which is just sort of going through from caudal to rostral, so from the back of the head to the front of the head, and you can see blood flow using color Doppler doing that. Now, a tool here that I want to point out are these. You can see them. I pre-drew them here just to save a little bit of time, but we have a region of interest that's been drawn here, and that region of interest is a 3D region of interest. It's not just like the 2D one. You can see it changes the shape. I drew it several contours around the right and left hemispheres of the brain. So those are actually 3D regions. So you go into the measurements, and that's what the tool looks like here, a 3D region. So that did exist for photoacoustic images before, but you can only ever draw one, which in a case like this, you know, where you want to be comparing left and right hemispheres, for example, you'd really want more than one. So that's what this tool allows you to do. You can see there are multiple regions here. You can see the colors. You can create a new one, and so on. So you can draw multiple 3D regions. So that's what I did here. I drew two 3D regions here. Now I'm going to go into split screen mode just by clicking down here to split screen. I'll go back to the study browser, and I'm going to bring up the oxygen saturation image. So I can't remember if, yeah, so this is actually, I've chosen the range here. I can go back here, but I've chosen the range here to be displaying between 50 and 100% oxygen saturation. And again, this is just a 3D during that ischemia. So we're able to visualize things here right down through the entire mouse brain. And these scans were done using the same parameters. So what I can now do, which is new in this version of the software, is I can right click, I can copy and paste those regions. So I can copy them one at a time like this, or I can just go in, do not hover over the region, hover over nothing essentially, and then I can say, okay, copy all ROIs, and I can paste them on this. So now I've got my two ROIs, which are identical to the ones because the scan is identical, and they're in the correct spot. So this saves tons and tons of time. You don't have to draw these multiple regions. You can just copy and paste them. And now we have all these different imaging parameters in the oxygen saturation image. So for example, we have all our 2D values for this particular slice, SO2 average. I'll just point that one out in particular. But then you can go down and you have all those 3D values as well. So the SO2 3D in the left hemisphere is 52, sorry, 57, and 50 in the right hemisphere. So we can see already that these are different. What I'm going to do now is I'm going to take both of these. I'm going to go back into the image processing panel. I'm going to say load into 3D. And now those regions are actually loaded into the software, into the 3D renderings of these things. So we can see now if we go to the what panel is that? The volume measurement panel. We can see both of those regions of interest that I drew in the 2D version are now copied over to the 3D version. And I can do that similarly on this one as well. Great. So now we've got both of those regions copied. Now, a few things here. I'm just going to make this a single panel. I'm going to look at the cube view just so it's a little bit easier to look at. And if I scroll through, there are my regions of interest there in the 3D renderings. I can then go in and do something like this, where I actually render those images. Do the same thing to both here. Okay, so now we have rendered images. Now, what if I just wanted to see the brain itself in this case? I don't want to see the skin. I don't want to see the skull. I don't want to see other tissue surrounding it. We have this sculpting tool. So you can go in and you can sort of shave off areas that you don't want to see in the image. we've added with the 3.2 software the ability to do a scalpel of the volumes that actually exist there. So you've essentially already drawn what you want to cut out. So it'll take everything outside of the region that you've drawn and discard it. So I can do that to both. Both here. Go into sculpting. Go into scalpel volume. So now I'm only looking at the brains of these two animals, so that it just makes visualization a little bit easier. You know, I can see, you know, these are now kind of nice to look at brain-shaped things if we're looking at the brain. So it just makes the visualization a lot neater. I can go down here and choose to display just the oxygen saturation. There's other, you know, imaging settings that I won't go into in great detail, but I kind of like looking at the MIP image in this case. And let's do the same thing here. So now we can see, you know, on the right hemisphere of these brains, there's significantly less blood flow and significantly lower oxygen saturation. Now there are different measurements here associated with the two regions that were copied over. This is percent vascularity. So it's just looking at of the volume, of that volume, how much of that volume is occupied by, in this case, Doppler signal, in this case, photoacoustic signal. So this is saying, okay, percent vascularity is 36 on the left hemisphere versus 20 on the right hemisphere. And it's what, 90% versus 76%. So there's significantly more photoacoustic signal in left versus right hemisphere in these cases too. So that kind of summarizes the ability to draw multiple regions, copy and paste regions, bring those regions into the rendered version, sculpt out areas outside of those regions that you don't necessarily want to see. And by the way, that all can be undone. So you can just, if I didn't want to do that, I can just undo it, and now we can see the regions appear again outside of that. I do want to point out one last thing here. I'll go back to the oxygen saturation image to do this. I'm going to get out of the split screen. So a new measurement that we've included is an SO2 histogram measurement. So again, by right-clicking on, hovering over the measurement, right-clicking, I can then go down and look at the SO2 histogram. So this is showing, you know, essentially how many pixels there are at a given SO2 value, okay? And right now it's only looking at one region, region 14, which is the left hemisphere, and it's looking at the whole volume. So now we can switch between the volume and the frame. So I can do this for each frame. I can generate a histogram and of course export that in CSV format, for example. Or as an image. And then I can switch to the right hemisphere and see the differences there. I'll toggle back and forth. So you can see the right hemisphere, that those peaks are shifted significantly over to the left, especially in, you know, certain, I imagine in certain slices where we see that more dramatically. You can, now the nice thing about histogram is you can do different kinds of measurements. You're not just looking at the mean essentially, or the average. You can look at the mode. You can look to see, for example, this is a, you know, basically has one mode, which is the peak essentially here. But if you look at this is on the left hemisphere. If you look in the right hemisphere, it has a similar peak around there, but it has another peak over here. So now you have this sort of bimodal distribution. So you can start to look at the stats of the histogram and pull out different things. And I want to switch back to my slides. Whoops. There we go. Oh, sorry. And here's an article that was published, I think last year by Jonathan May and out of Mike Kolios's group at Ryerson University. And they were actually one of the ones that inspired us to do some of this work, because they were able to see differences in essentially tumor heterogeneity. I won't go into great detail in this, but they were essentially able to see differences in tumor heterogeneity by looking at that histogram. And pull out some more subtle differences between some of the treatments that they were doing, and showing that, you know, some effects of the treatment versus the controls, they could really only see by looking at the histogram of some of these SO2 measurements. So this is just kind of a neat, use of the stats that you get from the histograms. So we've incorporated that into the software.
Okay, just before we break for questions, actually, I do want to pop back into Vevo Lab again to show a couple more things, because again, we've got so many great tools and add-ons in Vevo Lab. So a couple of things that I wanted to show that I had mentioned. One was the burst marker. So just to show what this is all about, I mentioned that this is very specifically for nonlinear contrast images. So this is a fairly long nonlinear contrast acquisition, and it has a burst here in the middle. So when you call up a nonlinear contrast image now, you'll see this extra added icon here that wasn't here before. Again, this is new in version 3.2. If we go to this, that's the burst marker editor. And it shows us that the system sees this burst happening starting at frame 931 and ending at frame 957, which if we sort of scroll through it, we can see is accurate. Every great once in a while, sometimes there might be a sort of timing issue, or especially with really long acquisitions, we can have trouble sometimes. And the marker on the system of where the burst actually happens might be off by a frame or two. It's very rare, does happen sometimes. So we've added this tool in so that you can edit those. And by editing something that's erroneous like that, it actually helps you to recover an image that wouldn't be analyzable previously, because if the burst is off a little bit, it will throw extra data into the analysis of the perfusion signal that would kind of mess up the analysis. So we're able to sort of recover images and then go ahead and analyze them. Another sort of little Easter egg, I didn't actually mention this before, but it's something that I thought of while Drew was speaking, is this is a new tab that we've added. I should actually show. If you go to Preferences, so go to the gear here in Preferences, there's this new Export tab. This allows you to customize the name that is generated when you export files. Now, this is the default string, and this is sort of what we've always had. This has been something that's been set in the background, where you have the image name, then year, month, date, hour, with a sort of a long timestamp behind it. But sometimes you might want to, say, have a particular study name or series name, or have an animal ID, or a particular type of naming convention that you've come up with to use for your exported images or your exported data. This is really nice if you're gathering a whole bunch of images together from a study that you're trying to put a paper or a poster or something together. So you can actually customize how those file names are generated, and it just helps you to organize your data and file things a little bit better. Did you
Okay, I just want to point out one more new feature that I talked about a little bit before. This is about the importing and exporting of spectral curves. So, I won't go into great detail here, but a workflow for doing some of these molecular imaging studies is to first characterize your photoacoustic contrast agent. I've just taken an example here using the Vevo laser to image. These are cross sections of these tubes that we use, and we have contrast agents in those tubes. You can see here that this is just a Bmode. Let me overlay them. So now you've got contrast agents in those tubes, and this is a spectroscan where essentially you're collecting data every 5 nanometers for the entire wavelength range. In this case, 680 to 970. So you can see changes in the absorption, changes in the photoacoustic signal that happen as a result of the difference in spectra of those contrast agents. So again, this all already exists, but you can see a graph. In this case, this is actually Evans blue, Evans blue dye, and this is a compound called PA trace. It's actually from a company called Nanohybrids. So it's a sort of a nanoparticle, essentially, which has a peak absorption out here. So these are great, and if you have the ability to have these agents and do this phantom experiment using the tools that that come with the system, this is great. And then you can save those spectra into the system, and you can use those to do your spectral unmixing. Well, what if you don't have access to an agent, or you want to use a curve from the literature, for example, to do your spectral unmixing, and you don't actually have one? So before, you could save the spectra, and after you save them, I'm going to go down here back into the study browser, back into the preferences. You would, after saving those spectra, they would exist in this PA spectral unmixing tab over here. And those curves would exist there. Now, let's say you didn't have those curves and you wanted to bring some in. There was really no way of doing that. Now what we've done is allowed the import of curves. So now we can say, okay, I want to import some curves. And by the way, I've already sort of generated these in a CSV type format. And you'll see a little message over here. Oh, there's 2 curves found, and here's what they are. Now, I just sort of exported these, and I'll show you this in a second, different methods to export. But now those have been imported into the system, and we can actually see what those curves look like here in the system and compare them to things like oxy and deoxyhemoglobin and so on. There's a little normalize function over here, so we can see how those curves differ. So then now I can go back into my multispectral acquisition. This is actually a neat study. Again, I won't go into great detail, but this is a kind of a neat study where we were doing a co-injection of these 2 dyes into the foot pad of a mouse and watching perfusion through the lymphatics. So I can then go into my spectral unmixing tab down here. This is, again, you're just looking at a multi-wavelength acquisition over time. I can select my dyes. I can select other chromophores in the image, such as oxy and deoxyhemoglobin, and then process those for doing spectral unmixing. Now, I mentioned before, if you generate the curves, you can export them, and you can export them in a format that Vevo LAB can read, so that you can export them from the system. For example, let's say you acquired your curves on the system, you can export them on the system, import them into Vevo LAB and work with them there. But we also allow you to export them in CSV format. So, for example, let's say you had a bit of motion during an acquisition that caused a bit of a spike in your spectrum that you know is an artifact. You can actually export it into CSV format, go into Excel or something, edit it to the curve that you know is correct, and then re-import it so that you have a correct curve for doing spectral unmixing. So I'm just going to change some of the colors of some of these things, just so that they're a little bit more easy to visualize. And then I'm going to overlay this. So this is, again, that injection of these different contrast agents. It's really bright, but you can see there right away that you have that's the PA trace contrast agent. I believe if I change the layers on this, you can see the Evans blue come in there as well. So this is, again, just a nice way of being able to import and export your curves so that you are able to visualize, do these multispectral imaging, visualize your components here. And I just want to, you can see the markers where the injection into the foot pad was performed, and then you can see the accumulation of these contrast agents going through the lymphatics. This is the popliteal lymph node, I believe. You can actually see differences in, neat differences in pharmacokinetics here, where you see the dye is going into the node, but then it's exiting the node as well. You can see the signal going up initially and then going down, versus the nanoparticle, which is accumulating. You can actually see even little sort of pockets of contrast agent that are being pumped through the lymphatics, and it's just accumulating in that lymph node there. Yeah, you can see things flowing in there. Sorry, I just thought that was neat. So that's again, that importing and exporting of curves in CSV and other formats is new with the 3.2 software.
All right, great. Thanks, Drew. So that sort of wraps up the presentation part. We'll get over now to some questions. So just bear with me for a second. Have there been any changes to the Vevo HD algorithms? No, not with this version. There was a substantial change to Vevo HD about 1 or 2 major versions ago, where we redid some of the speckle reduction and then also extended Vevo HD to include spatial compounding selectively in certain situations. But that was a couple of versions ago. So no, with 3.2, there's no major changes there. Couple of questions here about, I'll have to maybe get Drew to take these ones. SO2 average and average total, and can we apply SO2 measurement function other than brain, skeletal muscles?
Yeah, I mean, the second one's, well, they're both easy to answer. I'll answer the second one first. That SO2 measurement can be applied to essentially anywhere where there's blood. Photoacoustics is of course detecting the absorption of light and converting that into ultrasound. And blood absorbs light at the wavelengths that we're using with our laser. And you can, that's how the whole thing works and how you generate those oxygen saturation maps. So anywhere there's blood, you can measure SO2. What is the difference between SO2 average and SO2 average total? We do get this question quite frequently. SO2 average is the average within a region of interest of all of the colored pixels in an oxyhemo image. So it'll average each value of the colored pixels. SO2 average total will take every single pixel, whether it has photoacoustic signal or not, and take an average of that, with a pixel that has no signal being counted as 0% SO2. That measurement was added as sort of a bit of a surrogate for tissue oxygen. So you can imagine if you drew a large ROI and there was just one single pixel in that ROI, but it was 100% oxygen saturated, the average is going to be 100% SO2. And that's kind of hard to believe if you have a huge area in a tissue and there's only one pixel of blood in it. That seems strange to have an SO2 value of 100%. It's true for that one pixel of blood, but if you want a more global measure, say of an estimation of tissue oxygenation, then you want to count all the pixels and say, well, there's only one pixel that has oxygen in it, so the rest must be the tissue and the rest of it must be quite hypoxic.
First one was the difference between.
Yeah, I just
yeah. Okay, great. There's a question here about the Cine loop windowing. So this is actually something that we documented in the release notes, but we didn't actually talk about today. But since the question came up, I'll just show it briefly. So the release notes for 3.2 for lab mention Cine loop windowing for post-analysis. That's a really useful tool, as say for something like this in nonlinear contrast with going to Vevo CQ. If you have a Cine loop that's very long, like this one is, 1,860 frames, the Vevo CQ tool previously, well, it still does. If you tried to put this whole loop into Vevo CQ, it would only take the first 1,000 frames. And that's a limitation of the way that the software works. It's just simply not able to handle longer than 1,000 frames. And we were kind of stuck with that for a while. What you're able to do now is if you have a certain specific area within an image, because you can, with certain settings on the system, frame rate, and setting the size of the region box, you can potentially get up to a Cine loop that maxes out, I think, at up to 10,000 frames. So you have to be sort of selective. You can only analyze a 1,000 frame set. To choose a particular area that's 1,000 frames, you can take the handles that are here on the side, 1 or 1,860, and window that Cine down to a very particular area that you are interested in analyzing, whether it's, say, something like this, where you had an image that just before the burst, you're only interested in a little bit of information to get a baseline before the burst, and then after the burst, you want to see all of the reperfusion happening. So kind of choose your range. You might have to do a quick calculation on the side to figure out the 1,000 frames. Now, here, if you just clicked on Vevo CQ, it's still going to only take, this is a little bit of a trick. It's only going to take the first 1,000 frames because we haven't kind of saved this setting with this windowing. To do that, you have to click down here at the bottom on Cine Store. That effectively saves this image with this windowed setting. And now you go ahead and click Vevo CQ, and it will only take this set of frames that you have chosen instead of the whole thing. Now that applies also to Vevo Strain and Vevo VASC analysis as well. There are 1,000 frame limitations on those analysis packages. Again, it's just because of memory management and sort of overloading the software. There's only so much that it can really handle. So the same sort of approach applies there, where if you have a really long clip, you window it down to where you want to analyze, click Cine Store, and then go ahead and click on Vevo CQ or Vevo VASC or Vevo Strain. Okay, and just bear with me here for a second. I'm just going to bring the chat windows and question windows back up. One final question, because we are getting close to the top of the hour here. There's a question about whether or not we can sort the study manager by animal ID or by some of the other functions. So the short answer is no, not right now. That is something that we have kind of thought about. The fundamental way that the data is sorted and analyzed underneath in the file system, it's sorted by study name and by series name. I said name actually by date, sorry. So we're kind of stuck with that sort of approach, but what you could do instead is if you had a particular animal ID, if you wanted to bring up something really quickly, is say use the search box here. And just by typing in something that like I know I have several images in here that are named PSLAX for parasternal long axis, I can pretty quickly bring just those images up and then selectively review those. So practically anything that is saved with the images can be searched on. So whether it's the mode, in this case, say color Doppler, can be searched on. One of Drew's study here, the stroke study, has ischemia reperfusion. So if we knew that we had something like that, we could search and fairly quickly it comes up. Now, the larger your store of data where your Vevo Lab is pointing, it may take a little bit to search, but it does index the searches. So the first time it might be a little bit slower, but subsequent searches should be a lot faster. And yep, we're now pretty much right at the top of the hour. So I think we will wrap it up. There are a couple more questions coming there. Apologies, we kind of run out of time a little bit to get to those, but we will try to follow up by email later on to address all of those extra questions. So a couple of things that I just want to close with. One is to check out our Learning Hub that we have connected through from our VisualSonics website now, visualsonics.com. You can access our Learning Hub. We're starting to build out sets of training videos there where you can follow along, learn how to set up your animals, learn how to do basic cardio image acquisition or basic cardio analysis. We've been building out videos for 3D. We have longer term plans to build a whole series of videos for cardiovascular image acquisition and analysis, tumor image acquisition and analysis. So that would include things like 3D, power Doppler, nonlinear contrast. And Drew's got some plans for a whole series of photoacoustics analysis, acquisition and analysis videos too. Things like animal positioning, acquisition settings on the systems to really optimize acquiring your photoacoustics imaging data. Just to highlight an upcoming conference, it's coming up very soon, actually in a few days in Boston, if you happen to be in the Boston area or you're attending the World Farmweek conference in Boston. Mike Dunn from Regeneron Pharmaceuticals will be giving a presentation there. He's a longtime Vevo system user doing cardiovascular research and some other areas. He's will be, I'm sure, a very interesting presentation. Mike's a great speaker and quite a bright guy who's very experienced with the Vevo imaging system, ultrasound, and all of the capabilities and the tools that are at your disposal on your Vevo imaging systems. And just finally, please do try to connect with us. Check out our website, visualsonics.com. We do have a fairly thorough resource portal there for customers now. That's where we post webinars that we do. There'll be a recording of this webinar will be posted on our website in a short time. Lots of previous webinars are there. Documents, user manuals. That's also where we post our software updates as well. So if you want to go ahead and access the version 3.2 software that that Drew and I have been covering, that's where you'll find it at our website on the resource portal. Other information that's available on the website as well. I mentioned the webinars. We do maintain a presence on social. We've got a great YouTube channel that's got some really great videos on it. You can learn how to do all sorts of interesting things, catch up with us, see conferences that we've been at and sort of what's going on with VisualSonics. And then finally, I did mention a couple of conferences. We do attend globally a lot of different conferences, North America, Europe, Australia, New Zealand. There's lots of conferences going on that we attend. So check out the list that's there, that's coming up. If you see us at a booth at a conference, please stop by. We're always happy to talk to customers and see how are you making out with the tools. Is there anything that we can help you out with, and get some feedback. Product managers like Drew and myself are always happy to get feedback from customers. It's a great source of information of things that we can tweak and adjust and change and try to improve the product. So that's it. Thank you very much for joining us, and keep in touch.